enough laptops for everyone.
To me, it's evidence that there's not enough people, there's not enough people that have appropriate machinery to be able to do this. If you have to rely on those laptops that the workers are all running.
Yes. Okay, I'm gonna have to stop taking questions about this because I gotta start doing course stuff. But if you have opinions about this and you have not stated them verbally here, feel free to send me an email. And, or even if you have stated your opinion verbally, send me an email. And I can pass that along to the department and we will see what happens. We'll see if they'll listen to me. They won't necessarily, but we'll see what happens. Okay, any questions about anything else related to the course? All right. So, last time, what happened is that we left off with this definition of a function called BST put. And and this is a function that creates a new binary search tree that is like an existing binary search tree, except that there is one key value pair different. It either adds a new key value pair or it changes an existing one. And because we have data structures that are immutable, we have persistent data structures, we're not allowed to actually change anything. So we need to do this by copying pieces of an existing data structure. However, the idea here is that we want to copy as little as possible. And this is actually somewhat relevant to the current lab that we had yesterday. It would be nice if I had time to talk about this before the lab, but unfortunately the labs are scheduled for the beginning of the week rather than the end, so I didn't really have time. So I want to finish this today. Okay, so what's happening here? So the idea is that BST put takes the root of a binary search tree. So in other words, we're going to get something that looks like this. And we want to create a new binary search tree that is like the one that started at root, but key maps to values. The key maps to value. BST putting does all the work, and it's going to descend through subtrees of the binary search tree, making a copy of the existing tree as we go. But again, the idea is that we want to copy as little of the tree as possible. And what that means is we're really going to end up copying only the nodes that are along a single path. Okay? So, we have a couple of rules here. First rule says that if we start with an empty binary search tree, in other words, one with no nodes, we are going to return one that has only one node, and it maps key to value. And its two subtrees are empty. Okay? If we don't have an empty binary search tree, we have a non-empty one, and we will break that so there's a single node there. And we break that node into a key called other key, a value called other value, and a left and right subtree. Okay, so at this point, we can now start to do stuff. So the idea here is we're going to ask if key is less than other key. Okay, and so what that means is that if, I'm trying to get my right illustration here. So what that means, if the key we're trying to add is anywhere, it's going to be in the left subtree. It's going to be somewhere here. And so we will make a new node, which I've called non-empty BST. All right? And this is going to copy an existing node. So it's going to have other key and other value in it. All right? But now we have to be careful because I don't want to show you that yet. Now we have to be careful because we don't actually need to copy the whole tree. We only need to copy part of it. And what happens is that when we pass arguments to OCaml functions, we are passing pointers to those arguments. So if we just pass a value as an argument, we're not automatically making a copy. Okay, it's the same with other programming languages where if you pass a pointer to something, the thing you're pointing to doesn't get copied. Okay, so let's imagine here, we would like to add something in the left subtree. That means that we don't have to copy the right subtree at all. We can simply just reuse a pointer to it. Okay, so we'll write this. We're going to call BST putting with left subtree. That's the part that is going to copy a path along the left subtree. And then right subtree, we are not going to change at all. Okay? We're simply passing a pointer to that, and we don't need to copy the right subtree because we know that there can't possibly be any changes there. Okay? Does that make sense? Any questions about that? Go ahead.
What does BST putting left subtree return? Like, what is the value?
So what BST putting always returns is it returns a new binary search tree that is like subtree, but in which key is mapped to value. Okay? So here what's happening is we are returning something that is like left subtree, but somewhere in left subtree, key will be mapped to value instead of whatever it was before. Does that make sense? Other questions? Okay, and that's just what we want to be able to make this copy. By the way, I'm going to show an example of this that may make this a little clearer. Okay, else. Well, if key is not less than other key, maybe key is greater than other key. Other key is the one that's already at the node we're at. Okay, so now we know that if key is anywhere in the tree, it has to be in the right subtree. So that means we are going to copy the right subtree, but we want to keep the existing left subtree. All right, so again, we're going to say non-empty BST. That's going to create our new node. Okay, other key and other value, we know that those aren't going to change. Okay, and now what happens is that we will just simply use the existing left subtree, but we're going to copy the right subtree. Okay, two parentheses close that off. All right? And you'll note that there's a symmetry between these two paths, these two legs of the if. I mean, in the one case, what happens is we're copying the left subtree, in the other case, we're copying the right subtree. And in each case, the part that we don't copy, we're leaving those just as they are. And a good answer for a question, go ahead.
I think you missed a comma in the constructor call. Key less than other key, immediately after other value.
Okay, so what do I have here? Oh, yes, like that.
Yeah.
That's the one? Yeah, sorry about that. Anything else wrong? Any other questions? Okay, now, what happens if it's not less and it's not greater? Well, if it's not less and it's not greater, the only other possibility is that key is equal to other key, right? And that's because that's how total ordering works. And so we don't need to check for that. We already know it. So this is the situation where, let's imagine here's our binary search tree. And let's say maybe what we want to do is let's say we want to have key be 7. There's already a node here with key 7 in it. So all we want to do is make a new node that changes the value that 7 maps to. Okay? And values aren't shown on this tree, on that diagram, but they're there anyway. So what do? We're going to make a new node. non-empty BST. Okay, and now what's happening is we are going to add key and value there. Okay, so we've now got a node with both key and value. Okay, and we don't need to copy anything else at this point because everything below that node that had the existing key in it hasn't changed. So at this point, we are just going to say left subtree, comma, right subtree. All right. And so that's the end of this function. So then here there's an in that matches that let, and remember I'm using an internal helper here, so I don't have to keep passing key and value around because it doesn't change. What am I going to do? I'm going to call BST putin to do all the work. And I'm going to start with the root of the entire tree. So I'm going to start here. And, okay, two ugly semicolons at the end to tell OCaml that I'm done with the definition. Let's actually write this so it really looks like two semicolons. Okay, so there's our whole function. And again, the idea is that we are copying only the nodes that we need to. Okay, and I'm going to show an example about this, an example of this in a second, but any questions so far? Go ahead.
How would that placing the node? Because I know it's creating it, so how?
Okay, so the caller knows where to place the node. Because remember, the caller is either returning the new tree directly, or else it is sticking it in the left subtree of the node that it just created, or it's sticking it in the right subtree of the node that it just created. So this is one of the things that applicative programming, functional programming is a little bit different from imperative programming, where this function doesn't actually have to know what is being done with the new node it has just created. Its caller knows what to do with it. And so you can imagine now, actually, you can imagine a case where maybe we want to change the node we want to change the key and value at the node immediately at the root and nowhere else. This would still work. Then we would just create a new node that has the existing two subtrees in it. Okay, so it will end up working in the end. And did that answer your question? Other questions? Yes?
What does that align with the, after the second non-entity
Ooh, I'm gonna have trouble finding this. Right here? Right here? Right here? That? This one. This one. I'm really confused. Let me just, this one? Oh, cool. Okay, I was really confused. Okay, this is the start of, when you ask what does it say, is it that you just can't read my writing? What does it do? Oh, okay. This is the start of the rule that tests for a non-empty binary search tree. So what's happening here is, remember we've got this type. Let's see, do I have the type here anywhere? Here we go. So we've got a type here that says a BST has two constructors, empty BST and non-empty BST. Here we've got a rule that detects if we've got an empty BST, and it does this if we find it. Here's the one that detects if we've got a non-empty BST, and it does this on the right side of the arrow if we find it. Yes?
or style to keep you with keyword on its own line and then have the different options for it afterwards indented?
Okay, so OCaml is completely free format. like almost every other modern programming language, except for Python, okay? And so what happens is you can lay out code on the page any way you want. The only time that it would be poor style, I think, is if you're not consistent. So you should, if you find a way to lay code out on the page that you think is easy to read, that you like, if you're writing a long program, you should try to make the whole program look that way. But, you know, I mean, anything you can read, and for the fact that you're in a class, anything that the graders can read, I think is okay. But you should indent somehow or another to try to reflect the structure of the program. And go ahead.
Is BSD putting just able to access the value of key by nature of it being within BST put?
Yes.
You can pass it through as another parameter or anything?
Yes, that is exactly right. If I define one function inside of another, the internal function can see things that were set up by the inside function can see things that were set up by the outside function.
Then why do we have to pass through what as subtree?
Because subtree is changing.
Oh, okay.
Okay, so here, initially, it's root, but here it's the left subtree of an existing node, here it's the right subtree of an existing node. So subtree is not actually being inherited from the outermost function, it's actually being changed as BST pudding calls itself.
Oh, okay.
That make sense?
Yeah.
Other questions? Go ahead.
So like the vertical lines.
So the what line? Vertical line. Yeah, the vertical line that I drew there matches the let with the in. That's just to make it clear where the in, what let the in goes with.
Oh, no, not that one.
Not that one.
The one with the,
Ooh, okay. Oh, this one here.
Yeah.
Oh, okay. Yeah, that's a vertical bar like you get from a keyboard, and that's actually a real character there. That just serves to separate one rule from the other.
so if it's empty, key, it just says key value for none of them.
So, well, let me answer it a different way. If I have two rules in a match, I have to separate them by these vertical bars. Or if I have like 3 or 4 and some other, I have to separate them by the vertical bars. Otherwise, OCaml doesn't know where one rule ends and another rule starts.
So you could have more than two.
I can have as many rules as I want.
Okay.
I think all my examples so far have only had 2. You might need more than that for lab 3 from yesterday, though. I should really have an example. I'm going to show an example with multiple rules later today, if all goes well. Other questions? Yes?
Let's say you have 3 rules.
Uh-huh.
Can the program trigger more than one rule?
Not at once. The way that match with works is it tries the rules in order, boop, 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 like this, and as soon as it finds the first rule that succeeds, that is the one that it does. So it's kind of like an if then else, but different in that it works by pattern matching. So it's only doing, it can only do one, let's try again. It can only do one rule. Or, now it's possible you might get 0 rules. That's bad news because then the function won't return a value. And OCaml is actually able to detect that situation when it compiles your function, and it will warn you if that happens. You may have seen that in code that you've written. You get an error message that says, this is an incomplete match. And then it's sometimes able to come up with a situation where it says, you should have a rule that matches this, but you don't. Does that make sense? Other questions? Yes, go ahead. Okay, go ahead.
For the last, so like for the last iteration where it finds a place where it's supposed to put the key and value,
Uh-huh.
does it do that empty BSD?
Oh, okay. No, what it's doing is it's making a new, this will be clear when I do the example, by the way. What it's doing is it's making a new node that's like the node that it found, except that it's using a new key and value, and it's using the old left and right subtrees. And then it terminates, right, exactly, and then it terminates because there's no more recursive calls happening. By the way, there's two ways that that can happen. If it doesn't find the node with the key that it wants, it's going to end up here, because it'll eventually end up at an empty subtree. But if it does find a node with the key it wants, then it'll end up here. The other two cases are just used to move our attention down the tree. And somebody else had a question, and I don't know if you still want to ask. Oh, that was your question, okay. Okay, other questions? Good. All right, so let me try an example. So let's try to use this same tree. And let's say what I want to do is I want to add a key who's a node whose key is 6. Okay, so where's that going to go? Well, 6 is less than 10, so we're going to go here. 6 is greater than 5, so we'll go here. 6 is less than 7. That means we'll add a node right here with 6 in it. Okay? And so we're going to follow this sort of zigzag path through the tree. And what I want to claim is that we are only going to copy just the part of the tree that we actually need to make that happen. Okay, and I want to make another copy of this tree, just so I have room to write. So just bear with me here for a moment. So here we've got 5, 15. What did I have here? 2. Okay. And all of these blobs here, let's say, are just empty. Okay, we had 7 here. 15 here, so we had 13 here. And we had 20 here. This happens to be a well-balanced tree, but it doesn't need to be. And here's our root. Okay, let's see, have I made any mistakes? Anything good? Okay, this happens to be a well-balanced tree, but it doesn't need to be. It would still work, although with some less efficiency, on a tree that wasn't well-balanced. You know, let's say that was degenerate and just looked like a big, long, linked list. All right, so here's my function. Let's say what I want to do is I want to call BST put. I want to call that with a root, and I want to have 6, and I don't know what the value is going to be. I haven't shown values in my tree. Let's just write V here for value, just because I have to have something there. Okay? Now, what will this do? Well, it's not going to change the existing tree. It's going to return a new tree that will share some structure with the existing one. Okay, so let's see. Can I keep all of this stuff on the screen at once? Cool, I can. All right, so what's happening here is that here we're going to call BST pudding, and with root as my subtree. Okay, so now I'm going to go through here and I'll say, well, is root empty? It's not. So this rule is not relevant. It's not empty. So now what happens is that other key will be 10. Other value, we don't know what that is. Here's the left subtree, here's the right subtree. Okay? And my key here is going to be 6. So I'm going to ask if key is less than other key. Is 6 less than 10? It is. So what I now want to go down here. So let us call that S1. Okay. So what I will do then is I will call BST pudding with in the same way. Okay, so I'm here, I want to create a new node. There's my new node. Maybe I don't need S1. Maybe I do, we'll see. Okay, it's going to have other key in it, which is 10. Other value, I don't know what that is. And it's going to call BST pudding with left subtree, but its right subtree is going to point, that's not right. Its right subtree is going to point here. Okay, so we're now going to call BST pudding. And here we're going to call, I am going to call this S1 with S1. All right, and this is going to be the part of the tree that BST pudding is going to return. All right, now note what's happening here. We're going to build a new tree at this point by looking at the left subtree, but we have not copied the right subtree. We have simply, all we've done is we've simply stick a pointer to it into the new node that we just made. Okay, does that make sense so far? Any questions about that? Yes.
Do you consider this tail recursion?
This is, none of these are tail recursions. Well, okay, this is a tail recursion. This is a tail call. It's not a recursion, but it's a call. A tail call is the last thing that a function does. And what BST pudding is doing here is the last thing it does in every case is always to call a constructor. Now, in order to run that constructor, it might need to call itself recursively, but that recursive call is not the last thing it does, so it's not a tail call, not a tail recursion. Does that answer the question? Okay, other questions? Okay, so let's continue on. So now we're going to call BST pudding S1. We are still trying to add our key of 6, and our value, whatever that is just B. And so here, we are going to ask, is it empty? It's not. So here it's not empty. This is the rule that is going to run. And we know that other key is 5 and key is 6. So we'll ask, is 6 less than 5? And it's not. Okay, so we'll go down here. Is 6 greater than 5? It is. So we're going to create a new node. And this new node will end up being placed here. Why will it do that? Because the caller knows enough to, this is where the new node is going to be returned. The caller is going to know enough to put that where it should go. Okay, so we're going to call, and we're going to let other key be 5, other value be whatever that is. The left subtree is not going to change. So we will have the same left subtree, we won't copy it. The right subtree is where we're going to create the new node, and that is done by this other call to BST pudding. The right subtree here is S2, so we're going to call BST pudding with S2. Okay? All right, so does that make sense so far? Do people see why that worked? All right, I guess we're good. So now we'll come down here to S2. Is S2 empty? It's not. So we'll come here and we'll break this into 7 and a value we don't care about, a left subtree and a right subtree. Our key is 6. So we'll ask, is 6 less than 7? It is. So we are going to create a new node right at this point. And again, that will be added to this node when this call to BST pudding returns. And it's going to have other key and other value in it. So 7 is going to be here and whatever value was at that point. And, all right, and let's see. it's, all right, and it's, so 6 is less than 7. That means its right subtree is not gonna change. So here we go. And its left subtree is the one that we will recurse on. So that, we're gonna call that S3. So now we're gonna call BST pudding on S3. Okay, this example is about to finish, because we've just gotten to the case where we're not gonna do any more recursions. But any questions at this point? Okay, so now what happens? S3 is here. S3 is an empty subtree. So, what are we gonna do? Well, if we get an empty subtree, an empty BST, we are gonna create a new non-empty BST node. And the caller is going to put it there. And let's see, it's the key that we are adding is 6. That's our existing key. Its value is V, but we're not showing that on the diagram. And it has 2 empty subtrees, here and here. And at that point, all of this stuff starts returning. Okay, as these functions return, each function will return a new binary search tree, and the callers are, okay, and the caller knows what to do with those. It knows where to put them in the tree that it's building. Okay, so what do we have here? By the time all this returns, we are going to return that node. And so what we have is a binary search tree that looks like root, except that only one path through this tree has been copied. It shares structure with the existing tree. And the difference, the only new node that we have added is this one here at the bottom, like so. And which would make a lot more sense if you could have seen that. I hope you can see that. All right, so what's happened is that we've made a new tree, copying only the smallest pieces of the old tree that we need to, sharing nodes with the old tree that aren't copied. All right, questions about that? Does that make sense? Go ahead.
So every time you call non-empty BST,
Mm.
node,
Uh-huh.
and pass either left subtree or right subtree,
Mhm.
that's copy.
So it's, if I just pass left subtree without doing a recursive call, it does not copy. Because all I'm doing is passing a pointer. The copying occurs when I'm doing the recursive call. So what's happening here? So here when I'm passing right subtree, it's not copied. Here when I'm calling BST pudding, it is copying, because this call to BST pudding is going to be making a new node at some point. Okay, same thing is happening here. Left subtree is not copied, all I'm doing is passing a pointer. BST pudding, that is going to do some copying because it's, again, it's going to be making a node someplace. So that's the convention that I used. That's the convention that this function is following. Does that make sense? Okay, other questions? Go ahead.
When we're copying the subtree, what happens to the old, tree in memory? Is it written over? Does it
No.
still exist?
Nothing happens to it. So what we've got is persistent data structures, which means that a function like this does not change the existing tree. It's still sitting there in memory. It has to be, because maybe some other function still has a pointer to it. Okay, it also has to be because at this point, we don't have mutable data structures. So the only thing we can do is copy pieces of existing data structures with changes in them, but we want to copy as little as possible. Does that make sense? Go ahead.
I assume the garbage collector will then clean it up when there's pointers to it?
Yes, Now, that's actually a good point. So the question here was, will the garbage collector clean up after us? So a student asked about this at, last time after class. And they said something like, well, you know, isn't this awfully inefficient? Because, you know, what we've really got here is a couple different copies of things. And isn't it potentially inefficient to have all these copies? Well, I can answer that in two ways. First, memory is really cheap now. And, you know, this is not like, you know, this is not like 1970. So we might be able to afford to have lots of copies of stuff. Second thing is that let's imagine that this pointer here, root, let's imagine that goes away. Maybe the function that created that pointer returns, and so now there are no more pointers to this node. What will happen is the garbage collector will clean up the old nodes, it'll recycle them, and maybe the only nodes that will be left will be the ones that we created here, and the nodes in this tree that are pointed to by the ones we created. In that case, then we get a situation that is just as efficient as if we actually had side effects, as if we changed something. The garbage collector will get rid of the old tree, but it'll keep the new tree. Question in the back, go ahead.
Doesn't having 13 below 15 break the ordering of the tree?
Let's see, what do we have now?
The right subtree of 10.
Okay, so I think I probably copied it. It does actually. Let's make this, let's see, that has to be greater, so this, no, that's okay. So the idea is the left subtree is less than what's at the top. The right subtree is greater than what's at the top. So 13 is less than 15, 20 is greater than 15.
Wouldn't adding 13 put it to the right of 10, but that makes 15 a new left subtree?
So that it's at the right of 10, 13 is still greater than 10, so that's good. But let's see, I haven't actually changed anything on this side. So all I've done is I just have, here's the new node I've created, and just had a pointer to this subtree, but not changed anything over here. The only changes that I've made have been to the left subtree. Did that answer the question, or am I just trying to weasel out of it?
Just
Still confused. Well, okay, we could take this and try to redraw it.
It's not like the adding new nodes, it's just
Uh-huh.
like having the original tree built with 13 under 15.
Well, okay, so if we assume that the nodes